And now in this lecture we'll answer two questions. In the first question, we'll find out the value of angle AMQ is equals to x. We have to find out the size of angle AMQ is equals to x. We have to find out the value of angle x. And the second question, we find out the area of this circle that is inscribed by trapezoid ABCD. So we start with the first question. In the drawing we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. AB is the diameter. In the semicircle. In addition, we know that OS equals to SB. Inside this semicircle, we have square PQSO. Again, our task is to find out the size of angle AMQ that equals to x. We have to find out the value of angle x. So first of all, we know that all the angles in any square are right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is a right angle. AB is the diameter of this semicircle. AB is a diameter, it is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So integers here at the upper side of the straight line AB at point S, we have this angle that is a right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We know that all the sides of any square are equal to each other. So in square PQSO, side QS equals to side OS. QS equals to OS. You can write here that QS equals to OS. But it is given in the question that OS equals to SB. And for this equation, QS equals to OS equals to SB, we will derive that QS equals to SB. QS equals to SB. In the next step, we will do a construction. That is to say, we will join points B and Q together by a straight line. And we'll extend the straight line BQ until it touches the semicircle. We'll define the touching point of the extended straight line BQ with the semicircle. This point is point M. While doing this construction, we created the right triangle QSB. In the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, according to the rule that in front of equal sides in the triangle there are equal angles. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have in the right triangle QSB? We have y plus y is 2y plus 90 degrees. In total, they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Again, in the right triangle QSB, the sum of the angles must be equal to 180 degrees. That is to say, 2y plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from the equation, and here the 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2, and finally we get that the missing angle y equals to 90 degrees over 2 is 45 degrees. So actually, this is angle y is equals to 45 degrees in its size, and this is also angle y is equals to 45 degrees. In the next step, we'll join points M and N together by a straight line. And we'll join points N and N together by a straight line. By joining points N and A by a straight line, we find that triangle A and B. Triangle A and B subtend on A and B, that is the diameter of this semicircle, and therefore according to rule 7, triangle A and B must be equal to 90 degrees in its size. Repeat quickly on rule 7. According to rule 7, if the peripheral angle subtend on the diameter of the circle or a semicircle, then it is equal to 90 degrees in size. In the drawing we have a circle. This is peripheral angle ACB that subtend on chord AB, that is the diameter of this circle, and therefore according to this rule 7, it must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. In our drawing, we have triangle A and B that subtend on chord AB, that is the diameter of this semicircle, and therefore according to rule 7, triangle A and B must be equal to 90 degrees in its size. This is triangle ABN. Triangle ABN subtend on chord AN. Repeat again, triangle ABN subtend on this chord called AN. Likewise, this is triangle AMN. Triangle AMN also subtend on the same chord called AN. And because of the fact that those two triangles subtend on the same chord called AN, they must be equal to each other in their sizes according to rule 16. So I repeat quickly rule 16. According to rule 16, triangles that subtend on the same chord are equal to each other. In the drawing we have a circle. This is triangle A or B that subtend on chord AB. Likewise we have another triangle. This is triangle ACB that subtend on the same chord called AB. And because of the fact that those two triangles are both subtend on chord AB, they must be equal to each other in their sizes. That is to say, angle A, peripheral angle AOB equals to peripheral angle ACB, or alpha equals to beta. So if two or more peripheral angles subtend on the same chord, they must be equal to each other in their sizes. We can implement rule 16 in our drawing because of the fact that those two peripheral angles subtend on the same chord AN, they must be equal to each other in their sizes. But the size of this peripheral angle ABN is 45 degrees, and therefore the size of this peripheral angle AMN that subtend on the same chord AN must be also equal to 45 degrees in its size. According to rule 16, of course. In the right triangle A and B, this is the right triangle A and B. This angle equals to 45 degrees, this angle equals to 9 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their arcs, according to the rule that in front of equal angles in the triangle there are equal sides. So side AN equals to side NB. In the right triangle, triangle A and B, and therefore the right triangle, triangle A and B is also an isosceles triangle. So side N equals to side NB. So I write it down. We actually found out that triangle A and B is an isosceles triangle. Because side AN equals to side AB. Side AN equals to side NB. In the isosceles triangle, triangle A and B, AB is the best of this isosceles triangle, triangle A and B. Again, AB is the best of the isosceles triangle, triangle A and B. So if you know, AB is the best of the isosceles triangle, triangle A and B. But AB is also the diameter of this semicircle. AB is the diameter, it must be twice as long as the radius. So if the radius of this semicircle equals to R, the diameter must be equal to R. So AB is also the diameter of this semicircle, and therefore it is equal to 2R. So here we can implement rule 24 in our drawing. I please click on rule 24. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have the isosceles triangle, triangle ABC. Triangle ABC is an isosceles triangle because side AB equals to side AC. BC is the base of this isosceles triangle, triangle ABC. According to this rule 24, the perpendicular AO to the base BC bisect the base BC. First of all, AO is the perpendicular, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular AO to the base BC bisect the base BC. That is to say, it divides the base BC into two halves. Each half must be also equal, of course, equals to BC over 2. So the first half, BO equals to BC over 2. The second half, OC, must be also equals to BC over 2. So BO equals to OC equals to BC over 2. So we can actually implement rule 24 in our drawing. Why? Because in our drawing we have the isosceles triangle, triangle A and B. In the isosceles triangle, triangle A and B, the perpendicular from point N to the base AB, bisect the base AB according to rule 24. That is to say, divide the base AB into two halves. Each half must be equal to AB over 2. AB over 2 is 2R over 2, because AB is also the denominator. 2R over 2 is R. So each half must be equal to R, that is the radius of this semicircle. So the first half is AO, is equal to R, it is the radius of the semicircle, and the second half, OB, is also equal to R, that is the radius of this semicircle. But the question is, here is where the perpendicular from point M will touch the base AB. We know that AB, according to rule 24, the perpendicular from point N bisects the base AB. AB also equals to 2R. And AB is also the diameter of the semicircle. So the perpendicular from point N bisects the diameter. Therefore, if it bisects the diameter, it must touch the diameter at its midpoint. What is the midpoint of any diameter? The midpoint of any diameter is located in the center of the circle or a semicircle. In this case, the midpoint of the diameter AB located at point O, that is the center of the semicircle. Therefore, the perpendicular from point N to the base AB touch the base AB at point O, that is the center of the semicircle. So NO is the perpendicular, and therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction, and it touches the base AB at point O, that is the center of this semicircle. The first half AO is the radius, and the second half OB is also the radius of the semicircle. We know that the opposite sides of a square are parallel to each other. So in square PQSO, side PQ is parallel to the opposite side OS. So here we can implement rule 50. Repeat rule 50. According to rule 50, corresponding angles between parallel lines are equal to each other. In the drawing, we have line A that is parallel to line B. The red line C cuts the two parallel lines at those 2 points, and according to this rule, rule 50, those 2 angles are defined as corresponding angles, and because of the fact that they are located between the parallel lines A and B, they must be equal to each other and their sizes. That is to say, alpha equals to beta. So we can definitely implement rule 50 in our drawing, because in our drawing we have side OS is parallel to the opposite side PQ in square PQSO. Those 2 angles are defined as corresponding angles, those 2 angles, and are located between the parallel lines PQ and OS. And therefore they must be equal to each other in their sizes according to rule 50. But the size of this angle is 90 degrees, and therefore the size of this angle must be also equal to 90 degrees because they are equal to each other. In the next step, I will prove that in 2 different ways that quadrilateral NMQP, this is quadrilateral NMQP, is a cyclic quadrilateral. Repeat again, I will prove that quadrilateral NMQP is a cyclic quadrilateral. But first of all, what is the meaning of the sentence that a quadrilateral is a cyclic quadrilateral? A quadrilateral is a cyclic quadrilateral only if all its 4 vertices tap lie on the circle. This is the right quadrilateral ABCD. The right quadrilateral ABCD is inscribed by this circle. This is to say it is a cyclic quadrilateral because of the fact that all of its four vertices A, B, C, and D lie on the circle itself. You can see that all the four vertices lie on the circle. So a cyclic quadrilateral is a quadrilateral that all of its four vertices lie on the circle. On the circle that blocks the quadrilateral. So we have to prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be inscribed by a circle. It can be inscribed. It can be blocked by a circle. So I copied those two angles. This is angle NMP. That's subset on the base NP, and this is angle NMP. That is subset on the base NP, and we have also angle NQP. That's also subset on the same base NP. But first of all, we have to find out what is the value of this angle NQP. Actually, we joined points B and Q by straight line, then we extended the straight line BQ by straight line until we got line 7 BN. When you extend the straight line by straight line, the result must be a straight line. Therefore, BN is a straight line. So if we focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BN at point Q? You have this angle that is equal to 45 degrees in size. This is the right angle plus this missing angle. This is angle NQP. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. So now, in the left side of the straight line NB, at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line NB at point Q? We have this angle that is equal to 45 degrees in its size, plus this angle that is equal to 90 degrees in its size, plus the missing angle NQP. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. So 45 degrees plus 9 degrees plus angle NQP plus the size of angle NQP in total the must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees is 135 degrees plus the size of the missing angle NQP. In total they must be equal to 180 degrees according to rule 3. Here we'll subtract 135 degrees from this equation and we get that the size of the missing angle NQP is equal to 180 degrees minus 135 degrees is 45 degrees. So actually, this is the missing angle NQP that is equal to 45 degrees in its size. So we have to prove that quadrilateral NMQP is a cyclic quadrilateral. Repeat again. We have to prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, we can inscribe this quadrilateral NMQP by a circle. we have here those two angles. They are both equal to 45 degrees and they subtend on the base NP. Again, angle PMN equals to 45 degrees in its size and it subtend on chord NP. Likewise, this is angle NQP that is also equals to 45 degrees in its size and it subtend on the same base NP. So I actually copied those two angles in a new page. Those are the two angles with the coverage from the original drawing. This is angle NQP. This equals to 45 degrees in its size and it subtends on the base NP. Likewise, this is angle NMP. It is also equal to 45 degrees in its size and it subtends on the same base NP. So actually, if we block those two angles by a circle, it will obey to rule 16. Repeat again. If we block those two angles by a circle, like I did here, it will obey to rule 16. Repeat quickly on rule 16. According to rule 16, three angles that subtend on the same chord are equal to each other. So in the moment you have a circle, and this is peripheral angle AOB that subtend on chord AB. Likewise, this is peripheral angle ACB that subtend on the same chord called AB. And because of the fact that those two peripheral angles subtend on the same chord, they are equal to each other in their sizes. That is to say, again, peripheral angle AOB equals to peripheral angle ACB, or alpha equals to beta. So peripheral angles that subtend on the same chord are equal to each other in their sizes. So here we have peripheral angle NMP that subtend on chord NP. Likewise, we have peripheral angle NQP that is also subtend on the same chord called NP. And because of the fact that those two peripheral angles subtend on the same chord called NP, they must be equal to each other in their sizes. And indeed, they are equal to each other in their sizes. Each of them equals to 45 degrees and therefore they are equal to each other. And because of the fact that those two angles, if we inscribe them by a circle, it will obey to rule 16. It means that they are cyclic. It means that can be inscribed by a circle. Why? Because they obey to rule 16. Okay, so in the next step, I will join points M and Q together by straight line. Repeat again that those two angles, I copied them from the original drawing. So we join points M and Q together by straight line. So here we created quadrilateral NMQP. This is exactly the same quadrilateral NMQP from the original drawing. This is quadrilateral NMQP. We have the same quadrilateral NMQP that is definitely inscribed by this circle. Why? Because all of its four vertices N, M, Q, and P lie on the circle. And therefore this quadrilateral NMQP is inscribed by this circle. And therefore we can say that quadrilateral NMQP is a cyclic quadrilateral. Okay? So in the next step, we'll prove in the second way that this quadrilateral NMQP is a cyclic quadrilateral. First of all, we have here peripheral angle PQN that equals to 45 degrees inside and it's subtend of chord PN. The vertex of peripheral angle NQN is at point Q that lie on the circle. Likewise, we have peripheral angle PMN that is also equals to 45 degrees inside and subtend on chord Pn, and its vertex M lie on the circle itself. But what happens if we draw an angle that its vertex is outside this circle, like this angle PLN, and it's subtend on chord Pn. This is angle PLN that subtend on chord Pn. Its vertex L is located outside this circle. The size of this circle PLN, the size of this angle PLN is 39 degrees. That is less than 45 degrees. You can draw another angles that their vertices lie on the outside the circle and they subtend on chord Pn. They all will be less than 45 degrees. So you can say in general that all the angles that subtend on chord Pn and their vertices are located outside this circle will be less than 45 degrees. Like this angle, that is equal to 39 degrees. Likewise, if we draw an angle that subtend on chord Pn and its vertex is located inside this circle, like this angle PON, its subtend on chord Pn and its vertex A, its vertex O lie on the circle itself. The size of this angle is 85 degrees. So all the angles that their vertices are located inside this circle and they subtend on chord Pn will be greater than 45 degrees. So in general, we can say that all the angles that their vertices are located outside this circle and subtend on chord Pn will be less than 45 degrees, while all the angles that subtend on chord Pn and their vertices are located inside this circle will be greater than 45 degrees, like this angle PON is equal to 85 degrees. And therefore, only the angles that their vertices are located on the circle itself and the subtend on chord Pn will be equal to 45 degrees. Okay? So, I copied triangle NPQ from the original drawing. This is triangle NPQ that I copied from the original drawing. In triangle NPQ, angle NQP equals to 45 degrees in its size and it's subtend on the base NP. We have the rule that says that all the triangles are cyclic. That is to say, you can inscribe any triangle by a circle. Therefore, we can inscribe this triangle NPQ by a circle. We inscribe this triangle NPQ by this circle. So now we created triangle NQP. This is equals to 45 degrees in size and it's subtend on chord NP. According to the rule that I mentioned, only angles that their vertices lie on the circle itself and subtend on chord Pn will be equal to 45 degrees in their sizes. All the other angles that their vertices lie on outside this circle, or all the angles that vertices lie inside this circle will be either less than 45 degrees or more than 45 degrees. And therefore, all the angles that their vertices lie on the circle itself and they subtend on chord Pn will be located on the circle itself. So if we rotate triangle NQP around the vertex around this circle without changing its size, it will stay 45 degrees and the axis will not move. We will create infinite angles that each of them will be equal to 45 degrees in size. And one of the angles will be angle PMN, that is also equals to 45 degrees in size, and it's subtend on chord NP. So in this way, we created angle PMN, angle NMP, that is equals to 45 degrees in its size, and it's subtend on NP. Again, this is angle NMP. This is equals to 45 degrees inside, and it's outside on chord NP. So we join points M and Q together by a straight line. In this way, graded quadrilateral NMQP, that is definitely inscribed by this circle. Why? Because all of its four vertices, N, M, Q, and P, are located on the circle itself. Therefore, quadrilateral NMQP is exactly quadrilateral. Okay, so until now, I can find out that quadrilateral NMQP is exactly quadrilateral. We proved in two different ways that quadrilateral MNQP is a cyclic quadrilateral. This is quadrilateral NMQP, that is a cyclic quadrilateral. There also, I will block this quadrilateral NMQP by a circle. The red circle blocks quadrilateral NMQP because of the fact that all of the four vertices N, M, Q, and P are located on the red circle itself. Therefore, quadrilateral NMQP is blocked by this red circle. So here you can implement the rule that any cyclic quadrilateral, the sum of its two opposite angles is equal to 180 degrees. I put again on the rule. According to the rule, the sum of the opposite angles in a cyclic quadrilateral is equal to 180 degrees, or the sum of the two opposite angles of a cyclic quadrilateral is equal to 180 degrees. So according to the rule that I presented to you, the sum of those two opposite angles in the cyclic quadrilateral NMQP will be equal to 180 degrees. This is angle NPQ, that is the right angle, plus the opposite angle NMQ. In total, it must be equal to 180 degrees according to the rule that I presented to you. Angle NPQ plus the opposite angle NMQ, quadrilateral NMQP, must be equal to 180 degrees. Because again, that angle NPQ is a right angle, plus this is angle NMQ, is equals to 45 degrees plus x. In total, it must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees. So in total, this expression we have 135 degrees. In this side of the equation, we have 135 degrees plus x. X is the angle that we are looking for this question. Equals to 135 degrees plus x equals to 180 degrees. Here we subtract 135 degrees from this equation and get that the missing angle x equals to 180 degrees minus 135 degrees is 45 degrees. So the missing angle x, that is also defined as angle AMQ, equals to 45 degrees in its size. So angle AMQ is equal to x is equal to 45 degrees in its size. And that is the answer to the first question. In the next step, I present to you the second question and solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is trapezoid ABCD, or we can say it is a quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to side AB, and therefore quadrilateral ABCD is defined as a trapezoid because it has one pair of parallel sides. If we define the two opposite sides, the two parallel sides DC and AB are defined as the bases of this trapezoid ABCD. So if we define the length of the base DC as A and the length of the base AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height edge over 2. The height edge must create 90 degrees with its two parallel bases. So, again, the trapezoid is a quadrilateral with one pair of parallel sides, and the area of the trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B times the height edge over 2. And the height edge must create 90 degrees with its two parallel bases. So repeat again that in the drawing we have a circle that is described by trapezoid ABCD. In addition, we know that those two angles are both right angles. We know that side AB, the length of side AB of trapezoid ABCD equals to 3 units. And we also know that the area of this trapezoid ABCD is equal to 3 square units in its size. Again, our task is to find out the area of this circle that is described by trapezoid ABCD. So first of all, we'll define the relevant points of this question with letters. We'll define the center of this circle, this point as point O. We define the point of tendency of tangent DC with this circle. This point is point E. Likewise, we define the point of tendency of tangent DA with this circle. This point is point F. And finally, we define the point of tendency of tangent AB with this circle. This point is point G. We define the radius of this circle as X. In the next step, we join points O and G together by a straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of this circle, that is equals to X. So here we can implement rule 1 in our drawing. I repeat quickly on rule 1. According to rule 1, the tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle. This is tangent AB, that is tangent to this circle, that's point M. In addition, we have the radius OM, that equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OG that is equals to X. The radius OG is drawn to point G, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by a straight line. OF is of course the radius of this circle, that equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and E together by a straight line. OE is of course the radius of this circle, is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrangle DEOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4-piece angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4-piece angle must be equal to 90 degrees in its size. So in quadrangle DEOF we have 4 right angles, and therefore according to rule 5, any quadrangle that has 4 right angles must be at least a rectangle if it's a square. So we relate to quadrangle DEOF as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle DEOF, side EO must be equal to the opposite side DF, but EO equals to x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrangle FOGA, we have 1, 2, 3 rectangles, and therefore this 4-piece angle must be equal to 90 degrees. Therefore, can relate to quadrangle FOGA as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle FOGA, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA must be also equal to x units in its length. So the length of side DA, in total it is x plus x, that is 2x. DA is the side of a trapezoid, it is absolutely a straight line. We define the length of side DC of trapezoid ABCD as A. AB equals to 3 units in its length, if only to what is given as the equation, and CB is the missing side, so we leave it as it is. In the previous lecture, we proved that DA plus the opposite side CB equals to DC plus AB according to rule 2. So I'll not repeat on the same proof. We have only proved that DA plus CB is so in any trapezoid, DA plus the opposite side CB equals to DC plus the opposite side AB. repeat again. We have already proved that in trapezoid ABCD, DA plus CB equals to DC plus AB. DA is 2x plus CB. CB is the missing side, so leave it as it is. And it is equal to DC equals to A, according to our definition, plus AB. AB equals to 3 units in itself, according to what is the answer question. So in total, I should find out that x plus CB equals to A plus 3. Here we subtract 2x from this equation. And we get that CB equals to A plus B minus 2x. This is the missing side CB. This is equals to A plus B minus 2x units in its length. In the next step, we will do a construction. This is to say, from point C, we will draw perpendicular on AB. Again, from point C, we will draw perpendicular on AB. Okay, this angle comes to 90 degrees, and this angle also comes to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we created quadrangle DCMA. In quadrangle DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrangle DCMA we have 4 right angles, therefore can relate to quadrangle DCMA as a right angle according to rule 5. Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side AM. But DC is A, therefore the opposite side AM must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle DCMA, side DA must be equal to the opposite side CM, but DA is 2x, therefore CM must be the opposite side CM must be also equal to 2x units in its length. What is the length of line segment MB? MB equals to AB minus AM. So if you don't, you found out that the missing side MB equals to AB minus AM. So MB in total equals to AB, that is 3, minus AM, that is A. So in total, MB equals to 3 minus A units in its length. In the next step, I'll copy the right triangle CMB in a new page, and we will implement on this right triangle CMB the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is evaluation for Pythagoras theorem. So actually, this is the right triangle CMB as according to the original drawing. In this right triangle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. So I write it down. CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is A plus B minus 2x. Therefore, CB squared is A plus B minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared. Plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus 8 squared. So in total, we should find out that A plus B minus 2x squared equals to 4x squared plus 3 minus 8 squared. Here we will open the brackets on both sides of this equation according to the algebraic identity that states that A minus B squared equals to A squared plus B squared minus 2 times A times B. And therefore A plus B minus 2x squared will be equal to A plus B squared actually CB equals to A plus 3 minus 2x. Again, here, subtract CB from subtract 2x from this equation. And we should find out that CB equals to A plus 3 minus 2x squared. It is not B, but A plus 3 minus 2x squared. Again, CB equals to A plus 3 minus 2x squared. Here, CB equals to A plus 3, not B, but A plus 3 minus 2x squared. So, therefore CB squared will be equal to A plus 3, A plus 3 minus 2x squared. So A plus 3 minus 2x squared equals to A plus 3 squared plus 2x squared. 2x squared is 4x squared minus 2 times A plus 3 times 2x, and it equals to 4x squared plus 3 minus a squared. A plus 3 squared equals to a squared plus 3 squared, that is 9, plus 2 times a times 3, that is 6a, plus 4x squared. We have minus 2 times 2x is minus 4x. So in total this expression equals to minus 4x times a plus 3, and it is equal to 4x squared plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared minus 2 times 3 times 8, that is minus 6a. So here we have a squared on both sides of this equation, so a squared get cancelled. And we have 9 on both sides of this equation, so 9 also get cancelled. And we have 4x squared on both sides of this equation, so 4x squared also get cancelled. After we cancel all those expressions, in this side of the equation we left only with 6a. While on the other side of this 6a minus 4x times a plus 3. While on the other side of this equation we left only with minus 6a. So in total we have found out that (6a) minus 4x times a plus 3 equals to minus 6a. Here we will add 6a and also 4x plus a plus 3 simultaneously to this equation, and we get that 6a plus 6a is 12a equals to 4x times a plus 3. And again, we found out that 12a equals to 4x times a plus 3. Here we will divide this equation by 4, and finally get that 12a over 4 is 3a equals to 4x over 4 is x, so in total this expression equals to x times a plus 3. So we found out that 3a equals to x times a plus 3. Here we will divide this equation by a plus 3, and finally we get that x equals to 3a over a plus 3. Repeat again, we found out that x equals to 3a over a plus 3. In the next step, we will calculate the area of trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. So what is the area of trapezoid ABCD? The area of trapezoid ABCD is equal to the sum of its two parallel bases, that is to say DC plus AB, DC plus AB, times the height. The height is cm because it creates 90 degrees with the two parallel bases. So times the height cm over 2. And again, we found out that the area of trapezoid ABCD in total it is equal to the sum of its two parallel bases, that is to say DC plus AB, times the height cm over 2. DC is A plus AB. AB is 3 according to what is given as the question, times the height cm. Cm is 2x over 2. So in total, if you found out that the area of trapezoid ABCD is equal to, we have 2 in the numerator and 2 in the denominator, so 2 get cancelled, and we left only with a plus 3 times x. And again, if you found out that the area of trapezoid ABCD equals to a plus 3 times x square unit in its size. But it is given as the question that the area of this trapezoid ABCD is equal to 3 square units in its size. So we can substitute the area of trapezoid ABCD by 3 square units, and get that 3 equals to a plus 3 times x. Again, 3 equals to a plus 3 times x. But we already found out that x equals to 3a over a plus 3, so we can substitute x in this equation by 3a over a plus 3. We'll do it now and get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. So in total we found out that 3 equals to a plus 3 times 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled. After cancel a plus 3, we left only with 3. This equals to 3a. Here we divide this equation by 3 and get that a equals to 3 over 3, that is 1. So a equals to 1 unit in its length. We found out that a equals to 1, and we already found out that x equals to 3a over a plus 3. So now we can substitute a in this equation by 1, because a equals to 1. We'll do it now and we get that x equals to 3a. X equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 1. A is 1, so a plus 1 is 1 plus 3, that is 4. So in total, we actually found out that the radius of the circle, that its area that we're looking for, the radius of the circle x equals to 3/4 units in its length. Our task is to find out the area of this circle. You know that the area of any circle is equal to pi times the radius of the circle squared. Okay, again, the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3/4, and therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, we found out that the area that we are looking for in this question, that is the area of this circle, equals to either 9 pi over 16 square units in size, or in terms of numbers, the area of this circle is equal to 1.767 square units in its size. And that is the answer to the second question. So in the next step, I will start the lecture. I will start with the first question, of course. Our task in the first question was to find out the size of this angle AEMQ, this equals to x. We have to find out the value of angle x. So in the drawing we have a semicircle, point O is the center of this semicircle, AB is the diameter of this semicircle. We know that OS equals to SB, and inside this semicircle we have square PQSO. Again, our task is to find out the size of angle AEMQ, is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the square are right angles. So those four angles in square PQSO, they are all right angles. AB is the diameter of this semicircle. AB is the diameter. It is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We know that all the sides of any square are equal to each other. So in square PQSO, side QS equals to side SO. QS equals to OS, or SO. But it is given as the equation that OS equals to SB. OS equals to SB. And from this equation, QS equals to OS equals to SB, we derive that QS equals to SB. QS equals to SB. In the next step, we did a construction, that is to say, we joined points B and Q together by straight line. And then we extended the straight line BQ by straight line until it touches the semicircle. And we define the touching point of the extended straight line BQ with the semicircle. This point is point N. By doing this construction, we're going to do the right triangle QSB. In the right triangle QSB, in front of those two equal sides, we have those two angles that must be also equal to each other. Their sizes according to the rule that in front of equal sides in the triangle, they are equal angles. So if we define the size of this angle as y, then the size of this angle must be also equal to y, because they are equal to each other according to the rule that I mentioned. And we know that the sum of the angles in any triangle is equal to 180 degrees. It's true in any triangle, and therefore it is true in the right triangle QSB. So which angles we have in the right triangle QSB? We have y plus y, that is 2y plus 90 degrees, in total must be equal to 180 degrees. In the right triangle QSB, the sum of the angles must be equal to 180 degrees. That is to say, 2y plus 90 degrees equals to 180 degrees. Here we subtracted 90 degrees from the equation, and we found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divided this equation by 2, and we found out that the missing angle y equals to 90 degrees over 2, that is 45 degrees. So actually this is the missing angle y, this equals to 45 degrees inside, and this is also the missing angle y, that equals to 45 degrees inside. We know that we join points B and Q together by straight line, then we extended the straight line BQ by straight line, and the result is Bn. When you extend the straight line by straight line, the result Bn must be also a straight line. So Bn is a straight line. If you focus on the left side of the straight line, Bn is point Q, the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have on the left side of the straight line Bn is point Q? We have 45 degrees plus 90 degrees plus the missing angle NQP, total must be equal to 180 degrees according to rule 3. I'll repeat again. In the left side of the straight line NB at point Q, the sum of the angles must be equal to 180 degrees according to rule 3. That is to say 45 degrees plus 90 degrees plus the size of the missing angle NQP, total they must be equal to 180 degrees. 45 degrees plus 90 degrees, it is 135 degrees. So 135 degrees plus the size of the missing angle NQP, total must be equal to 180 degrees according to rule 3. Here we subtracted 135 degrees from this equation, and finally found out that the size of the missing angle NQP is 180 degrees minus 135 degrees. 180 degrees minus 135 degrees is 45 degrees. This is the angle NQP, and the size of this angle NQP is 45 degrees. In the next step, we join points M and N together by straight line, and also join points N and A together by straight line. By joining points N and A, we get peripheral angle A and B. This is peripheral angle A and B. Peripheral angle A and B subtend on A and B, that is the diameter of the semicircle, and according to rule 7, any peripheral angle that subtend on the diameter of the semicircle or a circle must be equal to 90 degrees in its size. And therefore peripheral angle A and B that subtend on the diameter of the circle is equal to 90 degrees. So in the right triangle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third angle must be equal to 45 degrees in its sides. So in the right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths. According to the rule that in front of equal angles in the triangle, there are equal sides. So AN equals to ANB in the right triangle A and B, therefore the right triangle A and B is also an isosceles triangle, because AN equals to ANB. And AB is the base of the isosceles triangle, triangle ANB. So here we can implement rule 24. Rule 24. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. In the drawing, we have the isosceles triangle, triangle ABC. ABC is an isosceles triangle because side AB equals to side AC. BC is the base of the isosceles triangle, triangle ABC. So, according to this rule, rule 24, the perpendicular from point A to the base BC, that is to say, the perpendicular AO to the base BC bisect the base BC. First of all, because of the fact that AO is perpendicular, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And the perpendicular AO bisect the base AC. That is to say, it divides the base BC into two halves. Each half must be equal to BC over 2. So the first half BO equals to BC over 2, the second half OC also equals to BC over 2, and of course BO equals to OC equals to BC over 2. So we can implement rule 24 in our drawing. For example, in our drawing, we have the isosceles triangle, triangle A and B. And the isosceles triangle, triangle A and B, AB is the base, and we know that AB is also the diameter of the semicircle. So if the radius of this semicircle is r, then the diameter must be equal to 2r. So, but the perpendicular from point N bisect the base AC. That is to say, the perpendicular from point N bisect the base AB. That is to say, it divides the base AB into two halves. Each half must be equal to AB over 2. AB over 2 is 2r over 2 because AB equals to 2r. AB is also the diameter of the semicircle, that equals to r. Because if the radius is r, then the diameter must be equal to 2r. So AB over 2 is 2r over 2, that is r. So each half is r. This is the radius of the circle. The first half is r, and the second half is also r. And the question is where the perpendicular from point N will touch the base AB. Because of the fact that the perpendicular from point N bisect the base AB, it means the perpendicular from point N must touch the base AB at its midpoint. What is the midpoint of AB? The midpoint of AB is the midpoint of the diameter AB, and you know that the midpoint of any diameter is located in the center of the circle or a semicircle. And therefore the midpoint of the from point N, the perpendicular from point N will touch side AB, it's its midpoint, that is the center of the semicircle, that is its point O. So the perpendicular NO bisects the base AB, divides it into two halves. Each half equals to r, that is the radius of the circle. So NO is the perpendicular, and therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We have the rule 50, that corresponding angles between parallel lines are equal to each other. We know that in any square, the opposite sides are parallel to each other. So in square PQS or side PQ is parallel to the opposite side OS. According to rule 50, in front according to rule 50, corresponding angles between parallel lines are equal to each other. Repeat again. Corresponding angles between parallel lines are equal to each other. those two angles are defined as corresponding angles and they are located between the parallels A and B and therefore they are equal to each other. That is to say, alpha equals to beta. We can implement rule 50 in our drawing. In our drawing we have those two corresponding angles. They are located between the parallels PQ and OS and therefore they are equal to each other. But this angle equals to 90 degrees and therefore this angle must be also equal to 90 degrees because they are equal to each other. In the next step, we implemented rule 16 in our drawing. In our drawing, we have those two angles that are defined as peripheral angles. They are both subtend or called AN. Peripheral angle ABN subtend on called AN, and peripheral angle AMN so also subtend on the same called AN. And according to rule 16, if two or more peripheral angles subtend on the same chord, they are equal to each other. Those two peripheral angles that subtend on the same chord, AN, must be equal to each other. But this angle equals to 45 degrees, and therefore this angle must be also equal to 45 degrees according to rule 16, because they subtend on the same chord called AN. In the next step, I prove that quadrilateral NMQP is a cyclic quadrilateral in two different ways. What is a cyclic quadrilateral? A cyclic quadrilateral is a quadrilateral that all of its four vertices lie on a circle. This is the red quadrilateral ABCD. The red quadrilateral ABCD is a cyclic quadrilateral because all of its four vertices lie on the circle itself. Okay, so in the next step we prove that quadrilateral NMQP is a cyclic quadrilateral using two different methods. In the first method, I copied those two angles, angle NMP and angle NQP, and in equate both those two angles subtend on the base NP. So actually, this is angle P NP. This is angle NMP. This is equals to 45 degrees inside, and it subtends on the base PN. Likewise, we have angle NQP. That is also equals to 45 degrees inside, and it subtends on the same chord called NP. So I copied those two angles from the original drawing. And those two actually inscribed those two angles by a circle, by this circle, and block them by this circle, and because of the fact that they obey to rule 16, from the fact that they obey to rule 16, we derive that they are cyclic. That is to say, we can block them by a circle. Why they obey to rule 16? Because of the fact that by blocking them by a circle, we can get two peripheral angles that subtend on chord NP. And according to rule 16, if two or more peripheral angles subtend on the same chord called NP, they are equal to each other. And indeed, those two peripheral angles that subtend on the same chord called NP, they are equal to each other. They are equal to 45 degrees, and therefore they are equal to each other. And because of the fact that they obey to rule 16, it means they are fit to a circle. They are cyclic. We can block them by a circle. So, in the next step, I join points M and Q together by straight line. In this way, we created quadrilateral NMQP. This is quadrilateral NMQP. This is like the quadrilateral from the original drawing. The scale is not the same, but it is the same quadrilateral NMQP. So I should prove that quadrilateral NMQP is definitely cyclic because all of its four vertices, N, M, Q, and P, lie on the circle. And therefore, quadrilateral NMQP is a cyclic quadrilateral. That is the first method. In the second method, that quadrilateral NMQP is a cyclic quadrilateral. First of all, I copied the triangle NMP from the original domain. In triangle NMP, we have angle. I copied triangle NQP from the original domain. In triangle NQP, angle NQP equals to 45 degrees in its side. So I copied this triangle NQP from the original domain, and we blocked this triangle by a circle. We know that all the triangles in the world are cyclic, and therefore can definitely block this triangle by a circle. So I block this triangle NQP by a circle. By blocking this triangle NQP by a circle, we created peripheral angle NQP that subtends on chord NP, and peripheral angle NQP equals to 45 degrees in its side. So here we have the same peripheral angle NQP that is equals to 45 degrees inside, and it subtends on chord NP. Here also peripheral angle NMP that is also equals to 45 degrees inside, and it subtends on the same chord called NP. You can see that the vertices of those two peripheral angles are both lie on the circle. But what happens about triangles, about angles, that their vertices are not lie on the circle itself, but outside this circle. Actually, you can check and see that all the angles that their vertices lie outside this circle and they subtend on chord NP will be less than 45 degrees. Like this angle NLP that subtends on NP. Angle NLP, its vertex is located outside the circle, and the size of angle NLP is 39 degrees, that is less than 45 degrees. It is true about all the angles that their vertices lie outside this circle. They will be less than 45 degrees. What happens about angles that subtend on chord NP, but their vertices are located inside this circle? Like this angle NOP, its vertex O lie inside this circle, and it subtends on chord NP. Actually, the size of this angle NOP is 85 degrees. So you can say in general that all the angles that their vertices is located inside this circle and they subtend on chord NP will be greater than 45 degrees. Like this angle NOP is equal to 85 degrees in its size. So all the angles that vertices lie outside this circle and subtend on chord PN will be less than 45 degrees, while all the angles that their vertices lie inside this circle and they subtend on chord NP will be greater than 45 degrees. So only and only the peripheral angles that their vertices lie on the circle itself and subtend on chord PN will be equal to 45 degrees. And therefore, if we rotate this peripheral angle NQP around this circle without changing its size, and the base NP is fixed, is located, is not moving, we create infinite angles that each of them will be equal to 45 degrees in its size, and they're all located on chord PN because the vertex PN is not moving. The axis PN is not moving, it is fixed. We move only the angle without changing its size and around this circle. One of the out of the infinite angles that we create will be angle PMN. Angle PMN equals to 45 degrees in size, and it's subtend on chord PN. It is exactly the same angle in PMN that is here. It is exactly the same angle. So we have here, we join points M and Q together by straight line. By joining points M and Q, we created quadrangle NMQP. This is quadrangle NMQP that is definitely inscribed by this circle. Why? Because of the fact that all the four vertices N, M, Q, and P are located on the circle itself. It is a cyclic quadrilateral. So this is a second way to prove that quadrilateral NMQP is a cyclic quadrilateral. So we shall prove that quadrilateral NMQP is a cyclic quadrilateral. This is quadrilateral NMQP. That is a cyclic quadrilateral. So we block this quadrilateral by this red circle. The red circle blocks this quadrilateral NMQP because of the fact that all of the four vertices of quadrilateral NMQP, they are all located on the red circle itself, and therefore quadrilateral NMQP is inscribed by this red circle. So here we can implement the rule that says that the sum of two opposite angles of a cyclic quadrilateral is equal to 180 degrees. So in the cyclic quadrilateral NMQP, the sum of those two opposite angles must be equal to 180 degrees. So in quadrilateral NMQP, angle NPQ plus the opposite angle NMQ must be equal to 180 degrees according to the rule that I presented to you. Angle NPQ is a right angle plus this opposite angle NMQ is 45 degrees plus x. Then again, angle NPQ equals to 90 degrees and angle, the opposite angle NMQ equals to 45 degrees plus x, and it is equals to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, so 135 degrees plus x equals to 180 degrees. Here we subtracted 135 degrees from this equation, and finally found out that 180 degrees minus 135 degrees is 45 degrees. So angle x, that is also defined as angle AMQ, equals to 45 degrees in its size. And that is the answer to the first question. In the next step, I presented you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is inscribed by trapezoid ABCD. So, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. If we define the two parallel sides, that is to say DC and AB is the basis of the trapezoid. Actually, the two parallel sides, DC and AB, are defined as the basis of the trapezoid. So if we define the length of the base DC as A and the length of the base AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B, times the height h over 2. So repeat again, a trapezoid is a quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases, that is to say A plus B in this case, times the height h over 2. The height h must create 90 degrees with the two parallel bases. So in the drawing we have trapezoid ABCD that blocks this circle, or this circle is inscribed by trapezoid ABCD. In addition, we know that those two angles are both equal to 90 degrees. Side AB equals to 3 units in its length. The area of this trapezoid ABCD is equal to 3 square units in its size. And our task is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, we define the relevant points to this question with letters. We define the center of this circle, this point is point O. We define the point of tendency of tangent DC with this circle, this point is point E. We define the point of tendency of tangent DA with this circle, this point is point F. We define the point of tendency of tangent AB with this circle, this point is point G. We also define the radius of this circle as X. In the next step, we join points O and G together by straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of the circle that is equals to x, according to our definition. The radius OG that is equals to x, the radius OG is drawn to point G, that is the point of tendency of tangent A and B with this circle. And whenever you have radius that is drawn to the point of tendency, then tangent A and B will be perpendicular to the radius GO. If A and B is perpendicular to GO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by straight line. OF is of course the radius of this circle, that is equals to x. According to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and D together by straight line. OE is of course the radius of this circle, that is equals to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrangle DEOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the side of this 4 pieces angle in total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrangle DEOF, we have 4 right angles, and therefore we can relate quadrangle DEOF as a right angle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in the small rectangle DEOF, side EO must be equal to the opposite side DF. But EO is x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrangle FOGH, we have 1, 2, 3 rectangles, and therefore this 4 pieces again must be equal to 90 degrees in its size. Therefore, we can relate to quadrangle FOGA as a rectangle because it has 4 right angles. But you also know that the opposite sides of rectangle are equal to each other. So in the small rectangle FOGA, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA must be also equal to x units in its length. Side DA in total equals to x plus x, that is 2x. We define the length of side DC as A. AB equals to 3 according to what is given in the equation, and CB is the missing side, so we will state it. We have already proved in the previous lecture that DA plus CB equals to DC plus AB according to rule 2. And again, we already proved that in trapezoid ABCD, DA plus the opposite side CB equals to DC plus the opposite side AB according to rule 2. DA is 2x plus CB is the missing side, so we will say this, and it is equals to DC is A plus AB is 3 according to what is given in the equation. So in total, we found out that 2x plus CB equals to A plus 3. Here we substitute 2x from this equation, and we found out that CB equals to A plus 3 minus 2x. This is the missing side CB, that is equals to A plus 3. A plus 3. CB equals to A plus 3 minus 2x. In the next step, we did the construction, that is to say, from point C, we draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we can relate quadrangle DCMA. Quadrangle DCMA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 pieces again, total must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees, and therefore this 4 pieces again must be equal to 90 degrees in its size. So inside quadrangle DCMA we have 4 rectangles, and therefore relate to quadrangle DCMA as a rectangle because it has 4 rectangles. But you also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. Likewise, according to the sum rule, in the sum rectangle DCMA, side DC must be equal to the opposite side AM. But DC is 8, therefore the opposite side AM must be also equal to 8 units in its length. What is the length of this missing line segment MB? MB equals to AB minus AM. MB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is 8. So in total, MB equals to 3 minus 8 units in its length. In the next step, I copied the right triangle CMB in a new page and we implemented the Pythagoras theorem on this right triangle CMB. According to the Pythagoras theorem, any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle CMB that I copied from the original drawing. From CB equals to a plus 3 minus 2x. So this is right angle CMB, that I told you earlier morning. This right angle CMB, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is a plus 3 minus 2x, therefore CB is a plus 3 minus 2x squared, and it equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared. 4x squared. Plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus a squared. So in total, if you found out that a plus 3 minus 2x squared equals to 4x squared plus 3 minus a squared. Here we open the brackets according to the algebraic of this on both sides of the equation. According to the algebraic identity, that says that a minus b squared equals to a squared plus b squared minus 2 times a times b. So according to the algebraic identity that I mentioned, a plus 3 minus 2x squared will be equal to a plus 3 squared plus 2x squared, that is 4x squared, minus 2 times a plus 3 times 2x. Again, a plus 3 squared plus 2x squared, that is 4x squared, minus 2 times a plus 3 times 2x. And it is equals to 4x squared plus 3 minus a squared. We open the brackets of this expression. A plus 3 squared equals to a squared plus 3 squared, that is 9, plus 2 times 8 times 3, that is 6a, and we have also plus 4x squared, minus 2 times 2x is minus 4x, so in total this expression equals to minus 4x times a plus 3, and it equals to 4x squared plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared, minus 2 times 3 times 8, that is minus 6a. We have a squared on both sides of this equation, so a squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled, and we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After cancel all those expressions, in this side of the equation we left only with 6a minus 4x times a plus 3, while on the other side of the equation we left only with minus 6a. So in total, if you found out that 6a equals to 4x, 6a minus 4x times a plus 3 equals to minus 6a. Here we added 6a and also 4x plus 4x times a plus 3 simultaneously into this equation, and finally found out that 6a plus 6a is 12a, so 12a equals to 4x times a plus 3. Here we divided this equation by 4, and finally found out that 12a over 4 is 3a, 4x over 4 is x, so in total this expression equals to x times a plus 3. So in total we found out that 3a equals to x times a plus 3. Here we divided the equation by a plus 3, and finally found out that x equals to 3a over a plus 3. Again, x equals to 3a over a plus 3. In the next step, we calculated the area of trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. And the area of trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB, times the height CM over 2. Repeat again, the area of trapezoid ABCD equals to the sum of its two parallel bases, that is to say DC plus AB, times the height CM over 2. DC is A, plus AB is 3, CM is 2x, divided by 2. So in total, if you found out that the area of trapezoid ABCD equals to A plus 3 times 2x over 2. We have 2 in the denominator and 2 in the denominator, 2, so 2 will get cancelled. After cancel 2, we left only with a plus 3 times x. So in total, if you found out that the area of trapezoid ABCD equals to a plus 3 times x, square unit in its size. But it is given as the question that the area of trapezoid ABCD equals to the area of trapezoid ABCD equals to 3 square units in its size. So you can substitute the area of trapezoid ABCD by 3 square units. We did it when we found out that 3 equals to a plus 3 times x. Here we divided, we only found out that x equals to 3a over a plus 3. Again, x equals to 3a over a plus 3. So we can substitute x in this equation by 3a over a plus 3. We did it, and we found out that 3 equals to a plus 3 times x, and x is 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 gets cancelled, and we're left only with 3 equals to 3a. Here we divided this equation by 3 and found out that a equals to 3 over 3 is 1. So we found out that a equals to 1, and we already found out that x equals to 3a over a plus x equals to 3a over a plus 3. So we can substitute a in this equation by 1, because a equals to 1. We did it, and we should find out that a equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 3. A is 1, so a plus 3 is 1 plus 3, that is 4. So in total we should find out that the radius of this circle, x equals to 3/4 units in its length. Our task is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 3/4, and therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total, we should find out that the area of this circle, that is the area that we are looking for this question, it is equal to either 9 pi over 16 square units in its size, or in terms of numbers, it is equal to 1.767 square units in its size. Okay, thank you very much.